Okay, welcome back, folks. Welcome back, folks. Good to see you all. So today we're continuing with our discussion about rasterization, but actually expanding the topic quite a bit. So lecture 3 today is an intro to signal processing. We'll continue this theme of sampling that we started last time and also introduce the really core notions and try to build them out more on aliasing and anti-aliasing. Particularly, I'm going to try to focus on the intuition for aliasing and anti-aliasing, especially in the 2D image sort of a sense. Okay. All right. Sampling. Sampling, as I described last time, so useful, very simple concept, right? It's just at a point, if you have a function that you want to know something about, sampling is just evaluating the function at that point, seeing what the value is. If you're doing it for a whole collection of points, that will be uniform periodic sampling. If it's on a grid or something. Sampling is ubiquitous in computer graphics and imaging. Let me give you a few examples to warm us up. So video, for example, you can think of as sampling in time. It's capturing an image of the scene, at a regular interval in time. Photographs, you can think of as sampling in a 2D sense on the image sensor plane. So here's a photo, part of a beach and a crab here. If you zoom in, as we've all done, right, from time to time, and look at the pixels themselves. Each pixel is what? It's the sum total of light at that position in the image, or the corresponding position in the image where it was on the sensor surface. And it's summing up the light, I guess, right, that arrives there through the lens from the scene brought there optically. We're going to study cameras later in the course, but just observe right now that each pixel is a sample of this image sensor lighting function at that position. We talked about rasterization last time, and I posed it, at least our first go at this, I posed it as sampling the inside triangle function, right, at an array of 2D positions, each of those positions corresponding to the pixel location in the frame buffer. Another thing that we're going to look at later in the course quite a lot is ray tracing and sampling light along light rays. Here's a little picture of that. We'll study this in a lot more detail later. You can assume you have some kind of pinhole camera model, so some kind of pinhole, implied pinhole here. There's a whole space of rays that can go out from there through like a viewing window to form an image. Here's one of those rays visualized as it flows into the world. And then here's a sort of cartoon for like some kind of object in the world, in this case, a marble statue. You can see that ray is going to go out and it's going to hit the marble statue somewhere. And I guess we're going to try to evaluate the lighting that comes back along that ray, right, towards the image. So that's a lighting function. And this ray tracing process is going to be sampling the space of rays. Okay, so ray tracing is sampling as well. When we calculate the color of an object in a scene, whether in ray tracing, or it turns out we'll see in rasterization too, when we talk about shading in rasterization graphics pipelines, we're going to have to do some lighting integrals. What does this mean? Okay, so here's a little cartoon as a camera. It's pointed at a particular surface element. It's this tiny patch of a surface. In this case, say the surface position here on this golden teapot, the top of this golden teapot. In order to calculate what the appearance of this golden patch looks like in the photograph in the direction, in a pixel in the direction of the camera, what we have to do is to sample all the different incident angles, all the directions that light could be arriving at this position on top of the golden teapot, and then figure out how much of that light reflects in the exact direction to go towards the camera. Okay, we have to do that, of course, for every position on the teapot. But for just this one position, we're going to sample all the incident angles that arrive at this one point on the teapot. Okay, that's sampling too. In this case, sampling the space of incident angles. So just a few examples of many ways we're going to use sampling in computer graphics and imaging. Now, sampling artifacts are also a central concern and ubiquitous issue in graphics and imaging. Let me show a few examples. You guys warmed up. Okay, we've all seen versions of this. It's called a wagon wheel illusion, right? It's a video false motion type of artifact. So here's a little video I'll play. All right, so it's just a piece of cardboard on a disc, okay, some kind of flexible thing. And if you spin it, I'm going to describe it. For those of you that might have different video resolutions than me through Zoom. Okay, I see the inner annulus. It's stopped moving. Now it's spinning backwards. Now the second annulus or disc is spinning backwards. Now the third one stopped and spinning backwards. And the fourth one's just stop motion and spinning backwards, and so on and so on. Each of the different regions or sectors of this disk apparently are turning at a totally different rate, or at least visually they're appearing to do that in this video, which is of course totally false because this is just a printout, right, on a piece of paper that's sitting on top of this cardboard disk. Okay, so time aliasing, false motion. Here's a different example. This one's called moire. It comes up in imaging from time to time, especially if you're thinking, trying to build image sensors, you're not doing a great job at it. Turns out this can come up when we do graphics and are using texture mapping. Texture mapping is taking images and trying to figure out how to paste them computationally on top of the surfaces that we're drawing in the world, like triangle meshes. Anyway, in this example, simpler, it's not texture mapping, it's just a straight up image. On the left is something that looks closer to reality. Okay, it's just a person who's wearing a blue shirt, has a very fine dot pattern on it, of blue dots in a white kind of cloth. On the right-hand side, you can see it looks totally weird. All right, you've probably seen versions of this from time to time. And how exactly did I make this image? Okay, so all I did was on the left-hand side, we're reading every sensor pixel. So every sensor pixel is showing up here in this image on the left-hand side. On the right-hand side, very simple. All I did was I just skipped the odd rows and the odd columns and only kept the remaining 1/4 of the pixels. So, okay, out of every 2x2 block of pixels, I only keep the, say, top left corner. And that produces the image on the right. Interesting. Now, this is, of course, a reduction in data, but there's different ways to do it that wouldn't cause this kind of aliasing at all. Let's talk about what's going on here. I mean, if you look at this blue checkerboard pattern, you see all kinds of really weird stuff that is not at all visually, realistic rendition of this shirt as we see it on the left-hand side. You see like a lot of, I don't know, in here, can you see here, there's like a kind of a weird, a pattern that looks broader horizontally than vertically. It sort of looks like it's stretched out horizontally. Over here, there's some kind of like pattern that looks as if it's like stripes of white in a blue, which is not the pattern on the left at all. In other areas down here, you can see a really fine looking, almost like checkerboard that is not the same frequency as over here. It's a higher frequency. In some areas, it's really low frequency. Over here, it almost looks like it's a light blue shirt, okay, instead of something that has this fine pattern on it. Weird. So this kind of spatially varying change in the appearance of a repeating kind of a pattern, this is called moire. Moire. Another example, Jaggies. We already looked at this, okay? This is the staircase pattern artifact that we saw in rasterization. So to remind us, okay, if you look closely at this sampling where we do a point sampling, one sample per pixel, in this case at the center of each pixel, and say, is it inside the triangle or outside the triangle, to color it, in this case, red or not. We see we get this kind of staircasing effect. Sometimes it looks like a perfect geometric staircase like this edge here. Sometimes it looks a lot more sort of raggedy, okay? Sometimes we get weird effects like isolated pixels. There's a lot of different patterns to it. It's not just a straight up geometric staircase, and very complex behaviors occur very quickly. This is also an aliasing error. It's a sampling error. This comes up not only in rasterization graphics, but it turns out it also comes up in ray tracing. Okay, so here's a ray tracing. I sort of sketched this description before. You can shoot rays sort of through a viewing plane out into a world and then sort of evaluate the light that comes back. We'll go into details about that later. But one point here is that, look, ray tracing is really good at this kind of an effect where you go through something that is going to refract the light. This is like some kind of glass object. So the rays that are going through there because of optical refraction are getting bent, right? And you can see that the checkerboard inside this, through this glass object, right? There's some kind of optical distortion to it. Can you see that? This is just a zoom in on this left-hand side. But it turns out, okay, this aliasing is not just a pattern because of the way that we set up triangle rasterization last time for 2D triangles. It turns out, even if you try to draw just this image pattern of a checkerboard, and even through optical distortion, look at that, you got Jaggies in here as well. Okay, maybe that's intuitive. Maybe that's a little bit surprising, but it's showing up in this very different form. This is not rasterization graphics. This is ray tracing. So to sum up, I showed a few examples of aliasing: Jaggies, which is sampling in space; the wagon wheel effect, which is sampling in time; moire, which is sampling of images, or in that case, subsampling, reducing the sampling rate of images. There are many, many, many more. The thing that ties all of these things together, and the way that I'd like for us to start thinking about it today, okay, is that a central part of when this problem is coming up is when we have a fast changing signal. Okay. The disk is spinning very quickly, or the pattern of the disks, of the black markings on the disk is spinning very quickly. The patterning in the shirt was varying very quickly in its blue dots. The edge of the triangle is changing from white to red abruptly, like in one step function. Okay, that's a fast changing signal at that boundary, so on and so forth. Okay, so we have a fast changing signal, which you can think of as high frequency. High frequency just means changing fast. Okay, and we're sampling. The case I'm going to make here is that we're sampling too slowly. We're sampling too slowly for a fast changing signal, and that's when this class of artifacts, this very broad class of sampling artifacts, is coming up. Okay. So again, the core of it is a fast changing signal, and we're sampling too slowly. That's the source of artifacting. And that leads me straight to the core idea. Okay, the core idea in this whole lecture. Okay, the core idea is deceptively simple, and yet it's extremely powerful. Okay, and this is the foundation of this lecture. Theoretically, a really powerful idea. The idea is to anti-alias. Anti-alias just means to take this aliasing error, this sampling, problem that we've looked at up to this point. Anti-alias means to take the opposite, because it's like get rid of the problem. It's a solution. Anti-alias means to get rid of aliasing. Okay, it's a positive thing. Okay, anti-aliasing, the core anti-aliasing idea is to filter out the high frequencies before we do the sampling. Okay, again, it's to filter out the high frequencies before we sample. Now, this should sort of make logical sense if you sort of buy my claim that the reason these artifacts are coming up, or we sort of notice that they're coming up when we have a fast varying signal and we're sampling too slowly. Okay, so fast varying signal, high frequency. If we filter out those high frequencies, that very fast rate of change before we do the sampling, then my claim is we can get rid of aliasing. And this is sort of by definition true. We're going to walk through exactly why it is in this lecture. But first, let me show you a couple of examples. Let's look at a video example first, okay? Let me show you an example of kind of a video. Again, we'll think of it as sampling in time. Let's compare point sampling in time versus anti-alias sampling in time. And to show it, I'm going to show you two videos, okay? This is just a freeze frame of each of them to let me explain it. So I'm going to show you one video where we're doing what I'll call a point sampling in time. The way this happens is that the video is not like super high frame rate. It's a 60 frame per second video. Both videos I'll show you are the same frame rate, 60 frames per second. But in the first video I'll show you, the one on the left here, the exposure, okay, the time that the camera is opening its shutter and closing its shutter for that one video frame is really short in time. It's 1/40th of a second. So it's almost like a freeze motion, okay? It's like only taking light from this tiny infinitesimal little, slice of time. And so you see things like as this droplet of, it's just a stream of water going into a cup here. As the stream is dropping down, it's so fast in exposure, you can actually see the individual droplets that are in this stream, okay? You see that on the left? The second video I'll show you, which has a freeze frame on the right-hand side, is just different in that the shutter is going to open and close for the full 1/60th second of that frame. Okay, so instead of 1/4000th of a second opening, it's going to be 1/60th of a second. Now the water is going down fast enough that over that 1/60th of a second, as you can see, it's going to blur out. Many droplets of water sort of went across, okay, that line, moved down that line over that 1/60th of a second. So you see a blurry stream. Does that make sense? Now what I'm going to claim here is that, okay, on the left-hand side, we're doing point sampling. So we have these high frequencies. We have this sampling too slowly compared to this fast moving signal, or this, this fast moving detail in this video here. And on the right-hand side, what we're going to be doing is filtering out that high frequency. We're blurring it out in time before we do the sampling. All the samplings at 1/60th of a second. Anush, question, please.
Hi. So, my question is about I'm trying to understand how let's say both of these two pictures, they capture a frame, right?
Mm-hmm.
Exposed differently. But let's say one of them is captured at 1/60th of an exposure.
Mm-hmm.
Does that imply that the time for which that frame is displayed in the video rendering has to be more has to obviously be more than the time of the exposure, right? Because
Just yeah, it could be the same or it needs to be just slightly long. You're right. It can't be shorter unless you do some computational imaging tricks, but that won't be important for the example I want to show today. So in
all
this
right,
case, you're right. It's 60 frames a second, and the exposure duration is 1/60th of a second, matching the frame rate. Okay.
all right, fine.
Yeah.
Thank you.
Okay. Let me show you the videos. Okay. Stravia, question.
Hi. So when you say that there's aliasing right here in the left image, what are you referring to?
Oh, we haven't seen the aliasing yet. We haven't seen
Oh,
the
okay.
hold your thought. Yeah, I have to show you the video so we see the see the aliasing. Good question. Okay, let me show you. Okay, so these are just freeze frames, a couple of frames, so I can show you the difference between the two videos and explain it. Let me show you the videos themselves. Now, I'm going to describe it again as I did for the wagon wheel effect because I'm not sure what you're going to see in Zoom because obviously Zoom's going to take my video feed and it's going to try to compress it and send it to you, and then the bandwidth may be good or not good, so it might change the video rate and all kinds of weird things might happen. This video I've noticed in the Kaltura recordings that I've seen online so far up to this point, they seem really high quality. They're sharp, high resolution, and they're good frame rate. So if what I described doesn't match what you're seeing, I encourage you to go check out the Kaltura recording afterwards to see it at the full rate. Okay. All right, here we go. So here's the first video. So the first video again is 1/4000th of a second exposure for each video frame, 60 frames per second. Okay, it's just a stream of water going into a glass. So what you see here is you see a whole bunch of droplets of water, in this stream coming down, but it looks totally weird. Okay, if you look closely, it actually looks like the droplets of water are actually maybe going up, sort of migrating up. They're sort of blobby and they sort of move around up and down. Okay. It doesn't look to me like a stream of water falling downwards towards the glass, which is obviously physically what's happening. Okay, so this is an example of time aliasing. Let's look at it in the stream sense. Okay, so here, okay, now it doesn't look like individual drops anymore. I can't see them; they're blurred out. Okay, but I see something that looks like water flowing down into like a glass of water, a stream of water flowing down into the glass. So in this anti-alias case, what I'm saying is that when I said the principle, right, is filter out the high frequencies, filter out the fast variation before we sample, this is what's happening, okay, functionally in this case as well. The 1/60th of a second exposure is blurring out that motion, the detail of this stream of water before we're doing the generation of the 60 frame per second video, okay? Or functionally, that's what's happening. Let me show you what it would mean, the same principle, if we tried to apply it, at least just at this level of intuition for now. We'll get into the math through the rest of this lecture. But intuitively, what do I mean for rasterization? Okay, point sampling, where we have aliasing, we've seen already. We have this triangle on the right-hand side. We sample it point by point to see whether different pixel positions are inside or outside. We color it red or white, whether it's inside or not. We get the answer on the right-hand side. Like we saw last lecture, we have aliasing, jaggies, okay? What anti-aliasing would mean intuitively in this case is to filter out the high frequencies, blur out the fast motion or fast, changing signal before we sample, which means we sort of insert like an intermediate step, if you will, sharp triangle, blurry triangle, okay? This is what I mean by getting rid of the high frequencies, getting rid of the fast varying in the signal, and then we sample, okay? That's the intuition I want to try to convey. And what you see on the right-hand side is that, okay, it doesn't look like much like a triangle. So we'll look at more examples, but this is an anti-alias rasterization of a triangle. What you see is that the pixel values are not just red or white anymore, inside or outside. You get sort of this partial this partial values along the boundary. Along the boundary, we see sort of pinkish or partially red values, okay? Let me pause here and take some questions and also look at the chat to see what's kind of going on. Some comments earlier about a beard. I think that's right on. I'm going to leave that. In the 40th, why is there a black line shadow? Oh, that's a good question. But in the 1/40th of second exposure video, there's a black line shadow moving upward. I could talk more about that. You're totally very observant. I'm going to leave that, and maybe we can talk about it in the comments on the website just for time, or come to office hours and chat about it more. It turns out that's an example of aliasing too, but I don't want to spend the time talking about it in lecture today because I have things a lot of stuff I want to cover. So sharp equals high frequency, blur equals low frequency. Thank you. Yes, that is the right intuition that I want you to take away. It's very simple, okay? A sharp boundary is a fast changing signal, right? It changes right at that boundary from white to red. That's a fast varying signal. That's high frequency change. Low frequency means it varied slowly, okay? It went sort of white to reddish to full red, okay? That's exactly it. Blurry means low frequency, okay. Okay. Anush, question?
Quick one. If I increase the FPS of the 1/40th second exposure to theoretically, if I did increase it to, uh, uh, yeah, like if I increase it, would it look fine?
Yeah, great question. If we increase the rate of that video, which was, each exposure is 1/40th of a second, instead of only capturing it at every, at 60 hertz, one every 60th of a second, what if we captured it really, really fast, like 4,000 times a second, okay? Would it look fine? What do you folks think? Who thinks it'll look fine? Not sure. Yeah, some people. It'll look weird, Allison says. I think it'd be great. I think it'll look fine. Good. I'm good. I'm glad you're thinking about it. Couple of comments. You could build a camera that would do that, actually. That'd be fine. There are cameras that can do that fast these days. To project it, to reproduce it on a display, that's pretty hard, maybe very cutting edge displays. Okay, so one observation is it's not easy. That's often why this issue comes up, is that we have a finite engineering rate that our systems can actually operate at, okay? So we have to be aware of this sampling issue because, or this aliasing effect, because the real sampling rates we can actually build are going to be finite, okay, and limited. But to the specific question, yes, if you could capture it at 4,000 frames per second and display it accurately at 4,000 frames per second, I think it would look great. I think it wouldn't look alias at all. I think you'd receive these droplets of water and they'd be very, your human visual system would sort of integrate that, and it would look like reality. Okay, look very close to reality.
Right.
Okay. Yeah. So increasing the sampling rate is fine too. Okay. I said anti-aliasing is if the problem again is high frequency, fast varying signals that we are sampling too slow. I said the anti-aliasing idea is to filter out the high frequencies before we sample. But if the problem is too low sampling, very natural. Another approach would be to just increase the sampling rate. Okay. But usually in our engineering systems, we can't do that infinitely. So it turns out that sampling and anti-aliasing problems always have to be considered at this anti-aliasing boundary at some point in practice. Okay. All right, let me keep going. I'll show you more pictures. So this was the cartoon idea I want you to have in mind. I think it seems to be getting anchored a little bit. I'm going to try to keep beating this idea. This is the intuition. Let's see some examples. This is point sampling. This is anti-aliasing. Okay. Point sampling, anti-aliasing. On the right-hand side, you can see lots of intermediate red values on the boundaries of these triangles. You can see lots of intermediate cyan to salmon colors along the boundaries of these cyan triangles. For those of you that are seeing this at high resolution accurately through zoom compression, you will notice on the left-hand side, that is where everything is really small. This is not a tiny effect. You can tell the jaggies go away. It looks way better on the left-hand side to do the anti-alias rendering, okay? The jaggies are visible even at low res, even at 1-to-1 pixel resolution. And these partial pixel values are visually very, very important in graphics and imaging. It works as well, okay, in the case of the ray tracing that I talked about. How exactly the anti-aliasing was implemented here is a non-trivial question. We're going to talk about it through this lecture, and the method that we end up going at the end will apply perfectly in this case. I won't talk about it further right here. I want to observe that it looks anti-alias, and you can see the elimination of the jaggies on the right-hand side, and make one simple point that, okay, you have to filter out the high frequencies before you sample. Okay, it doesn't work to sample and then try to filter out the high frequencies and then filter it or knock out high frequencies. If you do that, that's what's shown on the left-hand side. Okay, you sampled it and then you blurred it. Well, that looks like blurred jaggies. Okay, okay. The reason this comes up is that it can be quite challenging to filter out high frequencies before you sample. Just because that's the idea doesn't mean it's easy to build engineering systems that do that. Okay, so we'll talk about methods to try to do that, but you have to be very creative in many cases to accomplish it. Sampling and then blurring is trivial usually. Okay, you just do what you did before and then you just pass a low, just do some kind of blurring on it after the fact. It doesn't work. Doesn't get rid of aliasing. Okay, all right. So this lecture, that's the high level idea, the big core idea I want to try to get across. In this lecture, I want to dig into the fundamental reasons why this simple idea that I described works. And I want to look at how to implement anti-alias rasterization specifically. But that's actually going to be only a small section towards the end of this, this lecture. Okay. Take a quick look. If anyone has any questions that I don't see in the chat because there's so many, and I'm not particularly skilled at multitasking to read the chat and lecture at the same time, always feel free to just put up your hand and I'll call it out.
Sorry, Professor, could you explain again what is anti-alias rasterization, the concept?
Yeah, sure. Anti-alias rasterization is just going to be rasterization that is extended in a particular way to implement this core idea of anti-aliasing, which is filtering out the high frequencies in the signal before we sample in order to eliminate aliasing. And the aliasing in that case is called jaggies. Okay. So that's what anti-alias rendering. And it looks like this. So look, instead of this point sampling, this would be the anti-alias rendering result that we're looking for.
So what do you mean by high frequency? It's like the border or the edge of the shape?
So the high frequency change in rasterization, this is a very good question. So thank you. Reiterating this is good. So what is the frequency here again? What is this function? Like, what is the varying signal? The varying signal here, right, is the inside triangle function. It's a binary indicator function for whether you're inside the XY position, it's inside the function or not. It's fast varying in the sense that at this edge right here, where we transition from outside the triangle to inside the triangle, the signal changes discontinuously. It changes very, very quickly as you move in XY, right? From outside the triangle, binary to inside. That's a fast varying signal. And as we'll look at the frequencies of that kind of variation, we'll see that it's mathematically, we can consider it a high frequency signal, okay? But hold that thought about high frequency. I'll define it as part of what we're gonna do next in lecture. Wei Yu.
Thank you.
I have a quick question about previous slide. So there, the sign. Could you pull it back?
Sure. Which slide?
The previous slide.
This one?
No. One more. Previous. Oh, okay. Previous. No, I mean the one with that sign on there. We do anti-aliasing, point sampling. Cannot find. Oh yeah, this one. Okay, it's not previous. Sorry.
It's okay. I'm going back.
So if you go one more, and then there's a text. No, I mean there's a text on the below. There says 1 point per sampling.
I'm not sure where you.
You should take it offline. One sample per pixel. Yeah, here.
Yeah.
I'm wondering like how this change. Does we change like?
I'm going to cover that later. I'm going to cover that. That's at the end of the lecture. Yeah, hold that thought. Okay, let's keep going. Got a lot of stuff to cover. Okay, frequency space. Frequency space. So to get into talking about, the fundamental reasons why this works, I'm going to move into a phase of the lecture where we're going to lay a lot of mathematical structure in place for us to talk about this with the kind of language that I want to use, which is going to be in terms of the frequency spectrum and the frequencies of these signals. Frequencies are just going to mean the sines and cosines that we could use to decompose this signal, okay? But let's look at it with a little bit of scaffolding, okay? So what do I mean by frequencies? It's in terms of literally sines and cosines, cosine 2 pi x, sine 2 pi x. The frequency here is literally going to be what the frequency definition of a sinusoid is, okay? The rate at which it's changing. Specifically, if we have a function cosine 2 pi fx, then it has a frequency of f. So in particular, if f equals 1, we have cosine 2 pi x, which has a period of 1. Okay, so 1 sinusoid per unit interval. If we have f equals 2, then we have cosine of 4 pi x, which of course has 2 sinusoids, right? 2 oscillations in 1 unit interval. So these, we're going to refer to them as having a frequency of 1 or a frequency of 2, f equals 1, f equals 2. That's what I'm going to mean by frequency throughout this lecture, okay? You can have it for any integer or any real number as well. You could have a frequency of 1.5 in here. It would just be 1.5, sinusoids within a unit interval, okay? That's what I mean by frequency. Now, the next thing that I need to talk about is the Fourier transform. Now, some of you may have seen this in signals and systems classes before. It's okay if you haven't. You've probably heard of it before. In this class, we're really going to just use it at a very high level, conceptual level of its existence and what we can assume about the nature of signals because the Fourier transform exists. Okay, so I'm going to describe it a little bit and define it in the 1D case, but we're not going to test you on the math. We're doing a Fourier transform. We're going to ask you to calculate any Fourier transforms. It's really to allow us to get into looking at the frequency spectrum and analyzing what it looks like for intuition. What is the Fourier transform? The Fourier transform is a beautiful, right, idea, mathematical idea. It's an insight that we can decompose any function, almost any function. I mean, any function that we come up with almost in engineering, okay? That's some kind of real measurable function is going to satisfy the conditions to have a Fourier transform, which means that it can be decomposed exactly into a weighted sum of sines and cosines. Any function. This is a very strong and powerful idea that we can apply under very, very broad conditions, which I won't go into the mathematical, limits of or the theory of, but it's a very strong thing we can rely on. For example, we can have functions with lots of weird effects like, discontinuities, jumping in this square wave from 1 to 0. We can have very, very weird and, jumpy effects. And all of those actually under very broad conditions will be fine. They'll have a Fourier transform. In this example of a square wave function, the black function here, okay, that's oscillating from 0 to 1, let's just take a quick look at what this might sort of look like in the decomposition to sines and cosines. So here's the first two terms in the cosine decomposition. We have a constant a over 2 plus give me 1 second. And the first sinusoid here. And the sum of these two, the constant value in brown and this first sinusoid together gives us this function here. Okay, so this could be thought of as a first very low order poor approximation for the square wave function where we've only used 2 sinusoids. If we increase it to 3 sinusoids by adding this weighted sinusoid here in green of higher frequency, we get this sum here, which is a bit closer, and so on and so forth. If we add another cosine weighted appropriately, we can in this limit, get closer and closer to a sum approximation of that original function, which is a square wave. Since the Fourier transform exists for basically any function we care to put into it, and getting out the decomposition into sines and cosines, we can say at any point, if I give you a function, you can look into its sine and cosine decomposition and look at the frequencies, the energy of the different frequencies. Let's take a look at that. Okay, so if I give you an f of x, some function in the spatial domain, in this case in 1D, you can put it through a Fourier transform. Here's the mathematical definition of it. Again, we'll never ask you for it in this class or ask you to do any calculations of Fourier transforms, but it exists. In this case, e to the negative ix up here, right, is this notation, complex notation, cosec x plus I sine x. So this is a complex valued function. Again, not something that we're going to rely on in any substantive way in this class. So it's sort of a comment, a side comment. The Fourier transform exists to give us the Fourier transform exists to give us capital F of omega, which is the Fourier transform of f of x in something that we call the frequency domain or the Fourier domain. Capital F of omega we sometimes call the frequency spectrum. So it has a lot of different names. All it is taking the original input function and transforming it into the frequency domain to look at its frequencies. There also exists an inverse transform that's very well defined that could take us without loss from capital F of omega back to the original spatial domain function. Okay, so we can think of this as just looking at the original function in a completely different domain where it's equivalent, but gives us a view directly into its frequencies. Now again, what are the frequencies? The frequency is of any particular sinusoid is just the frequency of oscillation f that I looked at before, okay? And in the frequency domain, capital F of omega, omega is the frequency. It's a continuous value frequency index that we can look at. So if we put capital F of 1, the value of capital F of 1 is going to be the energy of this Fourier transform at frequency 1. If we put capital F of 2, that's the energy at frequency of 2, and so on and so forth. It's the weight of that sinusoid that we would be summing in that weighted sum to equal the original capital F of x. I'll come back to that and show you some 2D Fourier transforms and what the graphs of that look like, or the visualizations of that look like when we do image Fourier transforms and frequencies in just a few slides. Okay, we're going to do it very intuitively and graphically. Before that, let me make a couple of comments that connects this high frequency sampling thing, this high frequencies to faster sampling intuition that I described earlier. Let's just look at a few more pictures about it, okay? Higher frequencies just need faster sampling. Let's take a look at that. Again, so this f of 1 here is low frequency relative to the others on the page. F of 5 here is a high frequency sinusoid compared to the others. If we pick some sampling rate, okay, I just drew some dotted vertical lines here, some dotted vertical sampling locations here. We can see that if we sample these locations for this slow varying or low frequency sinusoid, those sample positions are giving us some reasonable approximation of the way it goes up and down, okay? It gets a little bit more error-like for the second one, which is higher frequency, and the error increases and increases to the point where when we have this high frequency signal here, the sampling locations that we have, if we try to interpolate between them, it doesn't capture at all the frequency or the rate of fluctuation of this f sub 5 of x. Okay, so this is the sense in which I mean higher frequencies need faster sampling. Very intuitive, okay? Let's look at this and realize something too, that actually if we sample any particular sinusoid too slowly, it might look like we're sampling a sinusoid of a lower frequency. Let's look at it, dissect this case here a little more carefully. Here's a high frequency sinusoid in blue. That's the real underlying signal. If we sample it at the locations according to these gray lines, then we get these sample positions here. You can see though, if we try to interpolate between these sample locations that we get, it could be just as easily explained by this lower resolution or this lower frequency sinusoid shown here. Okay, and if we don't know the underlying signal, all we're getting is sampling at these locations. We don't know the blue function. We just get these sample locations and we say, what do we think we have? The most reasonable explanation, but the simplest explanation would be this lower frequency sinusoid. What's going on here is that the two frequencies, the sinusoid of blue, which is high frequency, and the sinusoid in black, which is low frequency, these two frequencies are indistinguishable at the given sampling rate that I've drawn here. When that happens, those two indistinguishable frequencies, we call them aliases of one another. Okay, that's where this term aliasing comes from. Okay, so I want to explain the name a little bit. We call them aliases of one another. So what's an alias? Okay, an alias is just a false identity. Okay, this is the way to think about that, to remember this term. Okay, it's very literal actually. An alias is a false identity. Batman is Bruce Wayne's alias, right? He dresses up as Batman, which is a false identity to mask his true identity, which is Bruce Wayne, okay? So the black sinusoid that we see here, the low frequency one, is an alias for the blue frequency that we see here. Okay, they're indistinguishable, but one is not true. So when we sample too slowly, the problem that we have that we call aliasing, now you can understand what it means. We sample too slowly to capture the high frequency detail, and we incorrectly will perceive it in the signal reconstruction that we obtain as this low frequency signal when it's actually a high frequency one. Let's visualize more of this in the 2D domain, okay? In 2D frequency space and using images rather than 1D signals that I've used that so far. So I want to show you a whole bunch of pictures and try to start to build your visual intuition for 2D Fourier transforms and 2D frequencies and images, if you haven't seen this already before. So what I'm showing you here is a pair very similar to what I showed you before for 1D signals, but now we're going to do it photographically. So I'll show you a picture on the left of a baby, okay, a photograph. That's the spatial domain. Think of that as little f of xy. On the right-hand side, we've got the frequency domain. Each pixel in this 2D black graph here, so to speak, each of those is locations in that space represents a different frequency, a 2D frequency in space. I'll explain more in the next few slides visually. It represents a different 2D frequency, and the intensity of that graph there, if it's very bright, it means there's more energy at that frequency. If it's darker, it means there's less energy at that frequency. This is the visualization I'm going to use for the next dozen or so slides. Okay. Let me start to dissect this and give you a tour of the 2D Fourier domain, the 2D frequency domain. Again, those are synonyms, right? Frequency domain, Fourier domain, frequency spectrum, they all mean the same thing. They're just synonyms. Let me give you a tour. At the very center of this 2D frequency domain at coordinate 0, 0, this is the this is the sinusoid that has 2D sinusoid that has 0 frequency. What does 0 frequency mean? It means that it's varying very, very slowly, infinitely slowly. Does that make sense? Right? The lower the number, the lower the frequency, the slower it varies. So 0 frequency just means infinitely slow variation, which is a constant function. Okay, does that make sense? The constant function is just shown on the left-hand side by a grayscale value. Okay, unit the same over every part of the image. So this is the 2D frequency, 2D 0 frequency. Let's look at a sinusoid. In this case, it's a sinusoid in the horizontal direction. In fact, it's given by this function, sine of 2 pi over 32 times x. Sine of 2 pi over 32 times x. The frequency of this in the x direction is 1 over 32. Okay, if you remember that definition that I showed you before, okay, the frequency is 1 over 32. What does that mean? It means that in the sinusoids that you see in this image on the left-hand side, there are 32 pixels per cycle. 32 pixels per cycle. So in one of the white and black band pairs that you see here, there's 32 pixels across it. What that looks like in the frequency domain, you can see on the right-hand side here, it's turns out it's 3 dots. This is the frequency, the Fourier transform of this sinusoid on the left-hand side. I should also comment, it's not actually 3 blobs, it's just 3 dots. Okay, it's like 3 pixels that are turned on, but if I drew it that way, you wouldn't be able to see it. So I just drew dots so we can, for visualization purposes, okay? But this is the frequency domain representation of this sinusoid. What you observe is that it's 3 dots spread out horizontally. The maximum signal frequency of this location over here in frequency space is 1 over 32. The origin is 0, 0. The location of this thing over here is 1 over 32 in the x direction. Let's keep going. Let me show you another example. What if we double the frequency in the spatial dimension? So this is 2 pi over 16x. The frequency is 1 over 16 in this case. That means there's 16 pixels per cycle, so you'd expect it to be fluctuating faster. Okay, this is a higher frequency signal, as it is you see on the left-hand side. On the right-hand side, okay, it's higher frequency. That means it should be further away from the origin, which it is. Okay, this is 1 over 32. This is 1 over 64, 1 over 16, which is 1 over 16 is a larger number than 1 over 32, right? A little bit confusing with fractions, okay? It's twice as far from the origin, 1 over 16. All right, so that's the first thing you can see. Sinusoids correspond to specific locations on the frequency diagram. Let's orient ourselves. Okay, it's just symmetric vertically. So sine 2 pi over 16y is this kind of vertical location that you can see here. Okay, 1 over 16 distance vertically away from the origin. You can do things like cross products. Okay, sine of 2 pi over 32x times sine of 2 pi over 16y. It's just the cross product of these two sinusoids of varying frequency in the horizontal and the vertical direction. It looks as shown on the left-hand side. If you look closely, you'll notice that it's varying more slowly in the horizontal direction and more quickly in the vertical direction. If you look in the frequency domain, you'll notice that the energy, okay, at these points is located further away vertically from the origin and less far away horizontally. Okay, so this point here is higher vertically and less far away horizontally. Okay, this is just sort of getting the basic sort of lay of the land in frequency space. Okay, let's take a look at some other examples. Instead of simple sinusoids, let's look at a Gaussian. Okay, here's a Gaussian on the left-hand side. This is exponential of negative r squared over 16 squared. R is just, square root of x squared plus y squared here, just literally the radius distance from the origin on the image domain. It turns out this on the right-hand side is the Fourier transform on the left-hand side. It turns out to be a Gaussian too, okay? And it looks like this. Now, let me show you in comparison, okay, relatively. If we take this Gaussian on the left-hand side, let's say that we made it fatter. Okay, I just did it right here. You see that? So in the spatial domain, we just made the Gaussian fatter. Let's reason about what we think the Fourier transform should look like. Okay, we had a Gaussian that was shaped like this. It's varying at a certain rate, and then I spread it out horizontally. I want your intuition to be like, oh, that means that Gaussian is varying more slowly, okay? If it's kind of wider, it means it's not going up and down really quickly. That's high speed, that's high frequency. It's going up and down more slowly. Oh, that's lower frequency. So we would expect in the frequency domain intuitively that the energy would be concentrated to lower frequencies, which is exactly what we see here. So this is the higher frequency Gaussian that has energy that is spread out to higher frequencies on the frequency domain diagram. Okay, it's got energy out to further from the origin. And this is the slower, lower frequency Gaussian in the spatial domain, which means that its energy is concentrated towards lower frequencies, towards the origin in this frequency domain. Okay. You can do this anisotropically too. That just means, differently in X and Y. So here's an example. We squash it vertically. It's higher frequency now in the vertical direction. It's lower frequency variation in the horizontal direction. You can see exactly that in the frequency domain. We could rotate it. Okay, I did a kind of a kludgy way here. I said rotate 45 of this 2D image function, which I've shown you on the left-hand side here. And just the frequencies are going to vary. Okay, let's just reason this through. Okay, it varies slowly along this direction. Okay, in the spatial domain, it's going up and down more slowly in this axis. And if you look here, yeah, it's squashed towards the origin because it's squashed towards lower frequencies along this direction. It's going faster variation in this axis in the spatial domain, and in the frequency domain, yeah, okay, it's stretched out and it's got higher frequency energy in that directional axis. Okay. All right, so that's sort of a very laborious, just sort of like, let's look at some simple functions, orient ourselves in the frequency domain. Let me sum it up as further away from the origin, right? In the frequency domain, further from the origin here means higher frequency. That means stuff is varying more quickly. Closer to the origin in brightness means the energy is at lower frequencies, which correspond to things that are varying slowly in the spatial domain or the photograph domain. Let's go back and look at some more photographs. Yin, please ask a question.
Yeah, so I think when we were talking about the frequency domain, you mentioned some terms like energy, like brightness. Could you explain what you mean by those terms?
Yeah, thanks for the question. Think of this, I did use some terms there, so let me try to get mathematical for a second so we can be very precise about it. And sure, there's no mystery here at all, okay? When I say energy in the frequency domain at a specific frequency, I just mean what is the value of this frequency domain function at that pixel location. So if I pick a specific XY location in the frequency domain, that corresponds to a specific frequency, right? In X and frequency in Y. And what is the intensity of this picture at that XY location? That is the intensity of the Fourier transform there. And that's the intensity of that frequency. That's all I mean. And to get between the left image and the right image, we just perform this Fourier transform, which I gave the definition in 1D before. So it's like a function you can call a MATLAB, but we're not going to get into the mathematical details of that beyond what I've said already. Xiao, question.
Oh, it seems like you have two definitions of the energy. The first is like the intensity or the whiteness of the pixel. And the second is like how large you have in like the frequency domain. Because if you compare the slides, the small Gaussian with the large Gaussian, like there is sort of like a change in the size of the frequency domain, but in all the previous slides, all the points are in the same size, but just different intensity.
That's not intended. There are a couple of things you have to sweep under the rug here because the Fourier transform can be negative and other things, and I'm showing you an image. Okay, so there are certain things like that are simplified out. But if you think of them as, aside from, and also there's some complex values, so I'm simplifying that out to focus on the intuition of the shape of the distance from the origin. That's true. But the other comments you made, Xiao, about the size of this changing, how like it looks like it's spreading in and out or not. No, this is the function on the left is exponential negative r squared over 32 squared, where r is just square root of x squared plus y squared. Okay, just the radius. And you can calculate this image with exactly this definition, and then you can calculate a Fourier transform. And if you do that, you'll get exactly this image on the right-hand side. If you want to talk more about that, let's take it offline. Good questions, though. Iman, question.
Yeah, so I was wondering what it meant to have in the frequency domain, like sometimes, okay, for example, the spatial domain where there were the vertical white and black lines, you'd have in the frequency domains, the dots be horizontal. So I was wondering why the orientation is flipped in the spatial domain versus the frequency domain.
Here, great question. Thanks for asking it. Yeah, let's reason that through. Okay, so in this case, I showed first was the horizontal sinusoids. It was sine 2 pi over 16 of x. This is these are the slides you're referring to. Is that right?
Yeah, that's the one.
So, and I think your question is, why are they spreading out horizontally here as opposed to vertically here? Did I understand correctly the question?
Yeah, that's the question.
So, okay, so one comment is, so this is a fact, okay, mathematical fact. If you take the Fourier transform, it will turn out this way. But your question is a good one. Well, why is that exactly? Like, it looks like the sinusoids are stretching vertically, might be one intuition. So, but these points are spreading out horizontally. The way I want you to think about it intuitively, after that, we sort of have to get into the math, which I'm happy to do in office hours, okay? But the way you can think about it intuitively is that the variation in this case on the spatial domain, where is the variation happening? It's happening in the horizontal direction. And in fact, if you think about it vertically at any particular x location and think about the variation vertically, there is no variation, right? It's constant. It's either white or it's black vertically. All the variation or the frequency variation in this signal on the left-hand side is happening in the horizontal direction. That's why the frequency that carries that energy is located at a displacement in the x direction in the frequency domain, because that's what corresponds to this, and the higher the frequency, like the further we got in x, the faster the variation would be in the x direction in the spatial domain, and conversely for the y direction, okay? I hope that helped. If it didn't, let's take it up more slowly in office hours too. Okay, I'm happy to chat. Chetan, did I pronounce your name right?
Yeah, thanks. So I was wondering, like, why do we have like a mirror dots? Like, why do we need two dots, one on either side of the center one?
Yeah, good question. Why do we need it? It just turns out this is a mathematical fact about the nature of the Fourier transform. So it sort of gets into the details of that definition, the e to the negative I 2 pi, I fx thing. Anyway, the thing I showed, the definition of the Fourier transform, it's the way the math works out for the Fourier transform of a sine. For a cosine, it'd be slightly different. It wouldn't have the middle one. So for that, I think we would have to get into Fourier transforms, more into the math of Fourier transforms. So don't worry about that for now. Okay.
Okay, thank you.
You're welcome. Good questions. Okay, let's go back and look at some images and start to talk about filtering. I talked about filtering out high frequencies before we sample, right? I claimed that was the intuition about anti-aliasing. What does that even mean? Okay, so filtering in this case just means modifying, or let's think of it as like filter. What is it? Filter means to reduce or remove something, okay, from a collection. Filtering in this case is going to be removing or reducing frequencies, okay, in the frequency domain. So if I show you an image here on the left-hand side, and I show you its frequency domain representation on the right, this is the Fourier transform, we can look at certain filterings of it as follows. We could filter out all the low frequencies. I just deleted all the frequencies that are close to the origin on the frequency domain. This is the image on the left-hand side that corresponds to what remains, okay? This is the image that you see. What do you see? You see that what remains is the energy or the brightness, right? I had a question about what do I mean by energy? Energy just means the intensity, okay? In this case, in the hair, where there's a lot of very fine variation in the details of all the hairs, along edges, you can kind of see the outline of the clothing here or the shoulder, okay? What happens if we do the opposite, okay? We filter out all the high frequencies. So I took the original Fourier transform here, and what do? We just deleted everything above this disk close to the origin. What we've done is filter out all high frequencies except the very lowest, and this is the image that we get on the left-hand side. We see that it's got all the low, slow varying portions, right? But all the detail is lost. You can't see any detail in the hair, or the edges are all really broad and fat now, okay? This is what I mean by filtering. And this is what I mean by the corresponding effect in the frequency domain. So maybe this explains the intuition that I said before. The idea is to filter out high frequencies before we sample in order to try to anti-alias. Okay, let's I just want to do a little bit more of a tour here, and I want to take you through like a very detailed look, okay, of subsampling, like a much more detailed photo. So let me just show you. This is the lowest frequency band here. If we chose, just for fun, to keep this set of frequencies here, not the lowest and not the highest frequencies, just sort of a middle range, you can see what it looks like on the left-hand side. It's sort of like the mid-range variations. This is a little bit further from the origin. It's sort of getting tighter variations, okay, and so on. So you can kind of see that the further you get away from the origin, this is what maybe you can build continue to build your visual intuition. The further you are from the origin, the finer the rate of the fluctuations, the higher the frequencies of variation in the visual image. Now I said that, filter out high frequencies before sampling. I said filtering means, deleting these frequencies in the spatial domain or reducing them. I want to make a connection here to convolution. Convolution. I'm going to do most of this graphically, okay, visually, but I at least want to put up the definition and remind us of what that is in the 1D case. So bear with me for a few slides, and then I want to get back into sort of the visual graphical intuition slides. So what do I mean by convolution? Convolution, you might recall, many of you, I think, have been exposed to this in a signals and systems class. If you haven't, just sort of absorb this part, and then we'll move back into photograph space and 2D Fourier transforms in a second. A 1D convolution looks like this. I'll do an example first. So if you have a signal, say 1, 3, 5, 3, 7, 1, 3, 8, 6, 4. Okay, so a 1D array of values. And we want to take a 1D convolution with a particular filter. Here, I'll choose the filter to be 1, 2, 1. Convolution means that we take a weighted sum to get an output signal, a result signal, where the value of the output here is equal to the weighted sum of the original signal with the filter aligned at the output location. So in this case, the value 12 here is equal to 1 times 1 plus 2 times 3 plus 1 times 5. That's 12. And the next value here is 16. We slide over the filter one. So it's 1 times 3 plus 2 times 5 plus 1 times 3 gives us 16, and so on and so forth to get all the values in this output result signal. So we are given an input signal. We're given a filter kernel that we want to convolve against that input signal. And we perform this sliding weighted summation across the input 1D signal to get the output 1D signal in this case. The reason I want to remind us of this is because I want to show you on the next slide what the convolution theorem will show us in the 2D photograph case and derive a lot of visual intuition from that. Let me state the convolution theorem, very famous, very important convolution theorem here, okay? Convolution in the spatial domain, this sliding weighted averaging that I just talked about, is equal to multiplication in the frequency domain, and vice versa, although we won't make use of the vice versa part for today. So convolution in the spatial domain is equal to multiplication in the frequency domain, which means that we have two options for implementing a filtering in the frequency domain. We can filter by convolution in the spatial domain by the filter in question, or we can transform the filter into the frequency domain to get the Fourier transform of the filter, and we can multiply the Fourier transform of the convolution kernel and the signal in the frequency domain, and then transform back to the spatial domain. If you've seen convolution theorem, convolutions or Fourier transforms before, this will make perfect sense. If you haven't, this would be kind of a lot of word garbage. Let me try to show you a picture instead, okay? So this is what it means graphically for us in terms of photographs. We looked at in the spatial domain, and we talked about the frequency domain, its frequencies already. So I changed the orientation, okay? In this case, we have the image on the top, and we have the frequency domain at the bottom, because I need to go horizontal here. So the convolution theorem pictorially for us here means that if we have an input image, a 2D function, and we want to convolve it with this, say, square kernel here, this is just a function that's like a square function that's 1 inside the square and 0 outside. Which, by the way, if we do this convolution, it gives us, because we slide this window averaging over the whole photograph originally, and we average all the values that fit inside this little square to get the output value, the net effect of it, as you can see visually here, is to give us a blurry output image, okay? So the input image convolved with the square kernel gives us a blurry output photograph. In the frequency domain, what we can do is we can take the Fourier transform of the photograph, which I showed you before. You can take the Fourier transform of this kernel. You just treat this like a 2D function and look at its frequencies. It turns out these are the frequencies for this square top function here. And you can calculate the filtering or the convolution in the spatial domain. You can calculate its frequencies just by multiplying these two images together. So you don't have to do this 2D convolution, which is, takes quite a bit of computation. In the frequency domain, you can just say frequency by frequency, I'll just multiply every 2 pixel locations that correspond and write it out into this result image here. Okay, so this image here is this image times this image pixel by pixel. You get this image, it turns out that these two are also a Fourier transform pair. So you can take the inverse Fourier transform of this and get back to this blurry picture on the top here. So this gives you another kind of way to view the picture that we're, view the effect of filtering. I said filtering at high frequencies means we, reduce or attenuate or eliminate the higher frequency values, the ones away from the origin. You can see that if you do that, then it's similar to convolving in the frequency domain by some kind of kernel that results in a blurry image. Okay, so this sort of connects these two parts, what I mean by filtering and what's going on in the spatial domain. Okay, good. So I showed it to you pictorially over here. This is an example of like a box filter function that you could use as this kind of a kernel. This one's larger than 3 pixels across. Here's a 3 pixel example. This is a 2D box filter. It's just 0 everywhere except, in this set of 3 by 3 pixels, say at the origin, and multiplied by 1/9. So that's 1/9. So the area, so the average value or integrated area rather under this function is equal to 1, equal to unit energy. So it's a normalization. Now, a box function, which I showed you the picture of in this diagram here. So if you convolve these two, it's equal to this blurry picture over here. A box function, as you can see, is a low pass filter. Okay, it's a low pass filter because it's attenuating, it's only passing the low frequencies. This is what the term low pass means. Low pass filter, and it's deleting or it's not passing, it's filtering out the high frequencies. That's because this box function in the spatial domain has a frequency representation or a Fourier transform that looks like this. And just like we looked at the Gaussian case before, the same intuition applies here. If you choose a larger box function versus a smaller box function, that's creating a slower varying signal, okay, in the spatial domain. And that means that the energies in the frequency domain, where it's large, is getting compressed towards lower frequencies, as you can see over here, okay? So a smaller box function in the spatial domain means higher frequencies are going to pass. A larger box function in the spatial domain means that lower frequencies only will pass in the frequency domain. It also means that convolving with a larger box function is going to give us a blurrier output image. And this slide just says what I said before. Okay, so as a filter that's spread out in the spatial domain is spread out, localized in the spatial domain is spread out in the frequency domain. And a filter that is localized or compressed in the frequency domain is going to spread out in the spatial domain. Let me skip this slide. We're going to talk about it I left it in here for discussion on the website. Okay. The next thing I want to talk about is Nyquist frequency and anti-aliasing. So I give you this intuition, or tried to load this intuition into your brains at the beginning, that the idea for anti-aliasing is to filter out high frequencies before we sample. But of course, if you actually want to do it, you got to know, okay, well, filter out up to what frequency, okay? Filter high frequencies up to what number before I sample. There's going to be a connection between the sampling rate, how fast we're sampling, compared to the maximum frequency that we can allow, and we're going to filter our frequencies above that. The cutoff frequency for where we're going to filter high frequencies has a special name. It's called a Nyquist frequency. It comes from a theorem that relates when we will get aliasing and when we're safe from aliasing, okay? So Nyquist frequency and anti-aliasing is what I want to talk about next. This is based on something called the Nyquist theorem. Also a very famous and fundamental result in Fourier transform theory, frequency spectrum signal processing. I won't cover the proof in this course. This is a more mathematical result at a low level than is required for this class. But I want to state the theorem for you to extract the value of its precision. And then we're going to look at it visually and intuitively with a sequence of photographs. I want to show you what Nyquist frequency looks like, okay? Here's the theorem though first. The Nyquist theorem says that we get no aliasing from frequencies in the signal that are less than the Nyquist frequency. And the Nyquist frequency is defined as half the sampling frequency. Okay, there's a bit going on there. So let me say it again, and we're going to look at some examples. Again, we get no aliasing from frequencies in the signal that are less than the Nyquist frequency. What is the Nyquist frequency? It's just half the sampling frequency. So in practice, what this means is that if I tell you the rate at which we're going to sample, you take half of that, that's the Nyquist frequency. And our goal will be to go into the frequency domain and filter out all of the frequency domain that is higher than half the sampling frequency. So this theorem, which may take some time to sort of get familiar with this particulars. There's not a lot going on, as you can see, but reasoning about it takes a little bit of getting used to. The magic of it, the precision that it gives you, is that it answers the question: when I have a specific sampling rate, which frequencies am I supposed to filter out? What's the maximum frequency I can allow before I filter all the higher frequencies to avoid any aliasing? Let me show you an example. Let's go back to this example before. This was sine 2 pi over 32x, right? This is the sinusoid we looked at before, and I showed you that this is what the frequency domain looked like. Let's say we sample the signal in the frequency domain, in the image domain, as I show on the left-hand side. Let's sample it every 16 pixels. As you can see, like this is seems nice in the sense that it's going to capture every sort of white and black band in this image. So at least the sample signal is going to show black and white because we'll sort of capture the fact that it's going up and down. We'll see in the next example that if we sample more slowly, we might completely miss that, okay? The Nyquist frequency, if the sampling frequency here is 1 over 32, then, maximum frequency. Oh, sorry, I messed this up. The sampling is every 16 pixels, okay? So the sampling frequency is 1 over 16, okay? The sinusoid has a frequency of 1 over 32, which is plotted over here. But the sampling rate is 1 over 6, the sampling frequency is 1 over 16, which means that the Nyquist rate is half of that. Half of 1 over 16, as you can see, is 1 over 32. Okay, so the Nyquist frequency and the maximum frequency in the sinusoid match. So according to Nyquist, this is the exact cutoff when we're sort of safe, okay? No aliasing. Now, let's say though that we increase the frequency of this signal. We look at the case that we looked at before, sine of 2 pi over 16x. So in this case, the frequency is 1 over 16. That means we have 16 pixels per cycle. If we keep the sampling frequency at every 16 pixels, again, the Nyquist frequency is half of 1 over 16, which is 1 over 32. I've shown that as the separation still here as this red triangles, okay? Sorry, this here, so this right here. But the maximum frequency in this sinusoid is increased. It's twice as far from the origin. Okay, 1 over 16. So we're actually not safe. Remember, the Nyquist frequency says that we don't get aliasing from any frequencies below the Nyquist rate. But in this case, this signal, this sinusoid has frequencies that are higher. So we're kind of in a bit of a problem. Okay, we're not safe. And you can see it from the sampling rate. If you just look at the sampling on the left-hand side, what's happening? It's sort of obvious visually. All the samples are falling on top of the white, on top of the white bars. So the subsampling that we get would be a completely white image instead of one that has white and black going up and down. Okay. which means we've completely missed the fact that this is an undulating signal. We're sort of this is a classic sort of situation where we'll have an aliasing confusion. And there's one more example here, which I actually want to move on from. I'll leave this one. This example sort of just reiterates the point that I just made. I want to show you an example with real photographs. Okay, so let me show you a visual example with image frequencies and where the Nyquist frequency is. So I'm going to show you is a sequence of photographs at 512 by 512, and we're going to progressively blur that image, see how the frequency spectrum shrinks, and see what the maximum frequency looks like, and then we'll compare it to a sampling rate after that. So, but first, let me show you a photograph. This is the frequency domain on the right-hand side. If I start to blur it just a tiny, tiny little bit, I don't know if you can see that, it's not much yet, then this is the frequency domain on the right-hand side. So just the highest frequencies have gotten attenuated. The maximum signal frequency, so maybe out to here, is half. Why half? Because every pixel in this image is a sample. Okay, so the sampling rate is 1 sample per pixel. The Nyquist rate is half of that. So that's a half. It's a frequency of a half per pixel. Maybe that's the half here. That's not that important. Let's look at what happens when it keeps blurring. So this is, if we keep blurring it, it goes to a quarter. It's more blur on the right-hand side, an eighth, a 16th, and 1/32. So let me back it up. This is almost all of the frequencies retained in the image. As we're blurring more, now we have a truncation to half of those frequencies, half again, and half again. And the image on the left-hand side gets blurry and blurry as we do this. Okay, so that's all that's going on here. This is filtering out, filtering out frequencies closer and closer to the origin. Oh, one more, 1/64. Very, very blurry. Now let's look at what happens in that exact same image sequence when we sample the image. Okay, and we're going to sample this image at every 16 pixels. So let's take a look at this. Let's start with this picture here, the almost full resolution version. This is the sampling rate, the sampling grid on the left-hand side. Okay, this is every one sample every 16 pixels. I've also drawn what it looks like in the bottom here. Okay, so if you took this image on the left-hand side and you just kept every 16th pixel and every 16th row, you get this image in the bottom. I don't know if you can tell already, just by doing this totally simple sampling operation, you get something where you can see the aliasing really clearly. Okay, there's something clearly wrong with this image. You may have seen thumbnails that are created this way if they weren't created with good image processing. Now let's look at what happens when we, and I also drew the Nyquist frequency on here. 1/16 pixels on the left-hand side. The Nyquist frequency is half of that, is 1/32. It's this separation over here. So we have lots of frequencies that are way above the Nyquist rate, and we have aliasing. So as we blur more, we're bringing the maximum frequencies closer to the Nyquist frequency. We need to get it under the Nyquist frequency to be free from aliasing. Okay, we still have aliasing here, but the image on the left is a little blurrier. Look at what's happening in between these spatial, these sampling locations. This is a good example right here at this little detail of the hair of what's going wrong. This sample location is on the skin. This sample location is by chance right on the hair. This one here is over the skin. But in this row over here, even though the strand, this row up here, as you can see, we got skin, and we got skin over here. We've totally missed the band of hair that went in between. It's completely that fast varying up and down or darkness of the hair is completely lost because the sampling rate is too low. That's why we end up with these sort of weird looking artifacts in this subsample thumbnail here. Okay, let's keep going. The problem will disappear at some point if we blur more. In the frequency domain, the energy is getting closer and closer to the Nyquist rate. It's getting blurry in the frequency in the image domain. We still have a little bit of aliasing, but I think you can tell if I go back and down, it's getting a little bit less. Now we're getting quite close to the Nyquist frequency in terms of the max frequency over here is 1/16. The Nyquist is 1/32. This is Nyquist rate matching. It's quite blurry, as you can see on the left-hand side. We've had to blur it out a lot in order to bring the maximum frequencies filtered down to where the Nyquist rate is according to the theorem. This is the image that we get in the subsampling, and we have no more aliasing here. And if we go to 1/64, this is more than necessary. We've way over blurred the image, and the maximum frequency in the resulting signal is well under the Nyquist frequency. Okay. Let me just go back to the beginning and show it to you one more time. This is with all of the energy, very high resolution image. The subsampling produces a lot of aliasing, a lot of problems. As we subsample it and start to filter out the high frequencies, if we filter it more and more at a certain point close to the Nyquist frequency, we get to a level where aliasing completely disappears. But we pay a price. It starts to get blurry. And if we keep blurring it, it becomes way over blurry. Okay. Let me show that to you as a sequence over here. The Nyquist was over here. This is less blur. This is more blur before we did that sampling. There's strong aliasing over here. On this side, we have over blurring. You can take a look at this and try to think for yourselves about which one you prefer. There's a trade-off, okay, especially when you get close to the Nyquist rate, of whether you want more detail but have a little bit of residual aliasing, or whether you want to be completely safe from aliasing in a certain sense from Nyquist. But you know, this one may look a little soft or a little bit more blurry than necessary. And this slide here just makes the observation that this effect totally occurs even at small image sizes. Right. Let me take us back to how can we reduce aliasing error, okay, from this Nyquist theorem. We're safe if we have no frequencies above the Nyquist. The Nyquist is half of the sampling rate. So if we increase the sampling rate, we'll increase the Nyquist frequency. This means if we have high resolution displays, high resolution sensors, frame buffers, faster video cameras in time, that's faster sampling. And this will reduce aliasing. Okay, this is a question that someone had at the beginning on the video example that I showed. But it can be really costly. You need really high resolution engineering systems. And at some point, it may be impossible because you just can't make pixels that are too small, or you can't sample so quickly in time because you don't have enough light. So anti-aliasing, again, is at that boundary when you sample as quickly as you can afford to do so. The idea, again, is to remove signal frequencies above the Nyquist by this filtering process or this blurring process that we looked at before we sample. Okay, and again, for this rasterization case, we start with the triangle. Conceptually, we're going to blur it before we sample it, okay, in order to achieve an anti-aliased edge. So how are we going to do this? How are we going to filter out high frequencies in the rasterization case before we sample? We can use this thing that we've been developing this infrastructure for, specifically about filtering out in the frequency domain. This 1 pixel box width filter that I talked about earlier, I described we can try to convolve with a box filter in order to attenuate frequencies in the frequency spectrum. What we can do for rasterization is consider trying to convolve with a 1 pixel width box filter. Okay, so this filter here that we're going to try to blur the triangle with is going to have exactly the width of 1 pixel. In this picture, that box filter would be like kind of this square shape here. Okay, that's the area of it. And we'll try to blur this. Can you see how this blur looks roughly like the blur corresponding to moving a 1 pixel box over this triangle here? That's the kind of blurring effect or filtering effect level that we want before rasterization. This is what it looks like in the spatial domain. In the frequency domain, it might look something like this. So it attenuates the frequencies above a 1 pixel kind of sampling rate. When we do this, I want you to convince yourself of the following, okay, that these two things are the same. In fact, I'm going to start with option 2 because this has been brought up at the beginning of class in our pre-class discussion. It's on the website in some discussion. For anti-aliasing, many people have been saying, well, why do we compute the average value of f of xy inside the pixel, where f of xy was the inside triangle function? Why do we compute the coverage of that triangle area-wise or as a percentage of the area of this pixel that we're considering? I said, I think that's a pretty good idea. But why? And how do we sort of generalize that has been something we've been thinking about. Option 1 is, I'm saying convince yourself these are mathematically the same. Option 1 is convolve f of xy, that triangle function, by a 1 pixel box blur. And then we sample at the center of each pixel. That's option 1. Option 2 is compute the average value of that inside triangle function over the square extent of the pixel. I'm saying they're the same. I don't want you to go think about it and convince yourself geometrically that they're the same. Okay. If we do that, and I apologize, I have managed my time slightly poorly today. I think I'm going to stop here because we're at time. I'm going to connect this up to sort of practically what we do next, and I'll figure out how to do that. I think I'll just do it at the beginning of next lecture, or it's possible I'll send you a little video link to it as well. I'll think about that and I'll let you know. Okay. All right. Thanks a lot, folks. Good to see you, and I will see you again on Thursday. All right, folks. I just want to finish up recording here for this lecture on anti-aliasing. Okay, so as a recap of some things I just said at the end of lecture there. So we have the idea for rasterized or anti-alias rasterization, rather, is following exactly this general schema for anti-aliasing, which is to filter out high frequencies above the Nyquist limit before we sample. So in particular, if we rasterize this triangle onto this grid over here, then the idea is to blur it to filter out its high frequencies above the Nyquist right before we sample it in order to arrive at these partial pixel values along the boundary, okay? The question is, okay, how much blurring to do? And what I finished describing in lecture was that we can use or consider using a 1 pixel width box filter in the spatial domain in order to attenuate frequencies in the frequency domain whose period is less than or equal to 1 pixel width. This is practical to implement. You might sort of think about why. We're going to talk exactly about how we're going to approximate it practically in a second. Okay, but the idea here is if we have a box here, we can ask you to convince yourselves of these two things being the same. Option one was to take f of xy, where f of xy was that inside triangle function, convolve it, blur it by this 1 pixel box blur, then sample once at every center of the pixel for that blurry function. Option two was to take f of xy, the sharp triangle, inside triangle function, and for every pixel, compute the average value of f of xy in that pixel, which is sort of like the fractional coverage. Here's a picture of that. So if we have this being 1 pixel shown here, okay, in the top, in rasterizing the triangle, the average value inside the pixel area of f of xy would kind of look like this, okay? So if the triangle was white and it happened to cut across this pixel right through the middle of it, then part of it would be, say, black outside the triangle, white inside the triangle. Maybe this is another pixel where it cuts halfway through and so on and so forth. The filtered value then in this case for this pixel would be the average, right, value inside here. So a light gray going to a black in these 4 different cases visualized here in the top for the triangle cutting through this 1 pixel. Okay, so that's kind of the idea. Take the original triangle function, consider mathematically, interpret it as sort of convolving it with a 1 pixel box, and then sample, which is the same as taking the area coverage mathematically, at least I claim. The second step is that we're going to find a way to approximate this percentage area coverage that doesn't involve computing it exactly. Now, you folks are good engineers, so I bet if we said, hey, why don't you go and try to come up with a function to analytically compute exactly the geometric fraction of the area covered by of a pixel covered by a triangle, at least, or the pixel square covered by a triangle, I bet you could succeed at that. But for various reasons, it may not be very general. Like if we had a triangle that partially covered it, but wasn't like, a cover with just one edge over it, but it was like a triangle that sort of cut into it with a corner inside the triangle. Or if it was part of a tessellated mesh and you had one vertex inside that pixel so that there were multiple corners of triangles inside there, and you wanted to sort of consider, well, how do you calculate the partial area coverage in that case and add them all up? It can get a little hairy. So I want to propose a different approach, which is actually to approximate this anti-aliased answer that we're seeking by more sampling, or what we'll call super sampling. What is super sampling? It's a very simple idea. Super sampling is just the idea that instead of taking, one sample inside for one sample of every pixel, we could imagine taking multiple samples for each pixel. In particular, we can make the simple observation that we can approximate the effect of the one pixel box filter or the area coverage of the triangle over the pixel that I described. We can approximate those things by just sampling multiple locations inside the pixel, right? And averaging their values. That's what we call super sampling. For example, here is 4x4 super sampling. So we're taking 16 samples inside the nominal pixel boundary for this nominal square boundary for this pixel. Let me show you a pictorial cartoon example of this. Okay, so this is point sampling for a very small triangle on a patch of a frame buffer set of pixels. As we looked at last lecture, this would just give us zero values, or in the frame buffer for all these locations that are outside the triangle, and red for just these 5 locations where the centers are inside the triangle. If instead we did super sampling, say n by n super samples, in this case, say 2 by 2, okay, what we do is that for each of these sample locations, or each of these pixels, we break it up into 2 by 2 bins. We take 4 samples instead of 1, and we get this resulting sampling grid. We see that we have more samples that are inside the triangle in this case, but note that at this point we have a higher sampling grid, but every grid location still has a binary value inside or outside the triangle. It's either red or 0, or it's either red or gray, right? After this super sampling step 1, we have to do the second step, which is averaging down, because our frame buffer is not actually at this resolution, right? Our frame buffer is at the lower resolution. It's at the resolution of our final display. So we need to take the 2 by 2 samples in every pixel, and then we need to combine them to come with one output value. And the way that we would do it for this case is by simple averaging down. So we average those 2 by 2 values. We average these 2 by 2 values. This one here is interesting. We just go right across. When we get to this one right here, we can see that, go back. This pixel here has 3 samples inside and 1 sample outside the triangle. So we end up with a partial coverage here, and we can continue all this all the way through. Okay, this averaging down. The final values that we end up with the frame buffer are 75% here, 100% here. All 4 samples were inside the triangle, right? And here we have 50%, and this one had only 1 out of 4 samples of the super samples inside the triangle. This is the method used to produce the anti-alias super sampling that I showed you earlier. This is 1 sample per pixel. This is 4 by 4 super sampling with downsampling. Okay, so the final pixel value is the average of 16 samples within each pixel. So let me give you a summary of anti-aliasing by super sampling. Let me start again from the sort of foundations that we tried to build. Anti-aliasing is removing frequencies above the Nyquist before we sample. I made an observation a few slides ago that we can attenuate or reduce those frequencies above the Nyquist here. We can do that quite well with a 1 pixel box filter. That is convolution with a 1 pixel box filter. We can approximate that 1 pixel box sampling by super sampling within the pixel and then averaging down the values. And that super sampled anti-alias rendering. This is a simple idea. It's a good idea. It results in high image quality, although it can be costly, right? In that case, I showed you in the picture before, we had to sample 16 times more, right? To do 16 times more computation to achieve that anti-alias result. This approach of super sampling may feel right to you in a lot of ways. It may feel right to sample multiple times in each square and then sample down the values inside that square. But I just do want to make the statement that that's not a fixed, the right answer and a fixed solution for the best answer. Indeed, you can get even higher quality anti-aliased results by filtering in slightly more sophisticated ways even than this. And if you're interested in that, come chat with me in office hours. And I gave a few slides, extra slides at the end of this lecture that we could discuss, on the website that give some hints in the direction of these other approaches for even higher quality if you're interested. But for the remainder of this lecture, I just want to spend the time to just take a few minutes and give you some tips, okay, on super sampling implementation, because this is one of the things that you'll be building on your first assignment. So let me give you a couple of practical tips. Tip number one just has to do with the sample locations. I showed you this slide last lecture when we talked about point sampling. That's one sample per pixel. And I said, we'll ask you to follow the convention of taking the sampling at the geometric center of the square associated with that pixel. So for example, this is the pixel in the frame buffer for cell I, j, right? And we ask you to take the sample at the location I plus half, j plus half. When we do super sampling, say as an example, 2x2 super sampling, this is what the grid looks like. And I can just observe to you, so this is, again, the frame buffer pixel at cell I, j. The locations in the frame buffer are at these coordinates, okay? I plus a quarter, j plus a quarter for this one, and so on for these other locations. So you can reason about the exact continuous locations on this grid in this sort of a way. And I'll leave it as an exercise to generalize, exercise for you to generalize to the n by n super sampling case. Okay, but this cartoon diagram hopefully lays out exactly the way that you can visualize it. Tip number two has to do with what is the right answer, has to do with the issue of what is the right answer or what's the right approach when you have multiple triangles that you're rasterizing. How do you super sample a scene that has a whole collection of triangles in it? Okay, a mesh of some kind. I guess there's a couple of choices to consider. One option is, the question is, how should we change from rasterizing one single triangle where we super sample the grid and then average down? How should, we extend that or change it when we rasterize n triangles in the same exact image to the exact same frame buffer? One approach might be to super sample and average down each triangle one by one. Okay, so I take a triangle, I super sample it, average it down, put it into the frame buffer, go to the next triangle, repeat. Another approach might be super sample all n triangles onto the same high resolution grid in one shot, and then average down at the end after I've rasterized all of the triangles. I've super sampled all the triangles. Okay, so those are two different sort of strategies. Which is the right answer? I want you to go think about it, feel free to chat about it, and sort of figure out what the right answer is. Okay, but this is something important if you want images to look right as you rasterize full scenes. What are the algorithmic implications of this is something that you're going to work through in implementing this. For example, what's the minimum memory that's needed in order to implement super sampling of scenes in general? And the last slide that I have in the formal section of this is just that there's much, much more to sampling theory and practice. This is one lecture on the connection between signal processing, in particular the theories around frequency domain, aliasing, anti-aliasing, Nyquist frequency, and their connection to sampling in computer graphics and imaging. But there's entire courses that you could take on sampling theory and signal processing practice related to that, and it's an incredibly rich topic. Okay, so this is the things to remember slide that I add to the end of every one of our lectures for you on the website for review. Feel free to consult this. I know it's going to be in every lecture. Great to see you all again today, and I look forward to seeing you on Thursday. Bye-bye.